Hello everyone. So far in this week related to seismic design and ductile detailing of reinforced concrete buildings, we have looked into seismic design and ductile detailing of RC beams. We have also illustrated the same using an example problem. In today's class, we will continue our discussion with seismic design of reinforced concrete columns. So when we are looking into reinforced concrete columns, we should be preferring rectangular or circular columns at max. We should be avoiding irregular shaped columns such as T-shaped and X-shaped. The minimum column dimension shall be equal to 20 times the diameter of the largest longitudinal bar used in the beam in any of the beams which are supported by the column, or 300 mm, whichever is larger. Further, the cross-sectional aspect ratio of the column shall not be less than 0.4, which means that the width of the column shall not be less than 40% of the depth of the column. If it is so, it will be classified as a shear wall. We will look into shear walls in the upcoming week. These illustrations show the minimum column width in case of the exterior column and an interior column. Now, when we are designing an RC column for good seismic resistance, we need to ensure that there is a failure in form of plastic hinges in case of beams before any failure in the column. How can that be enforced? That is enforced through weak beam strong column hypothesis. How? For that, we need to have the columns which shall have more strength than the ultimate capacity of the beam. For that, the sum of nominal design strength of columns meeting at a joint along each principal plane should be at least 1.4 times the sum of nominal design strength of beams meeting at that joint in the respective plane. So, when we are talking of seismic resistance of any building in the x direction, then in that case for a given joint there can be two columns, one from top and one from bottom. If it is the top story, there will be only one column from the bottom, and similarly there can be at max two beams in the same plane, one from left, another from right. If it is an exterior column, at that joint you shall have only one beam. So, you sum the moment carrying capacity of all the beams at that very joint, you sum the nominal design strength of column at that point, then the sum of the nominal design strength of column shall be at least 1.4 times the sum of nominal design strength of the beam. Here we can see that for this, these two columns added together should be more than 1.4 times the design strength of this beam and this beam. Similarly, the sum of the design strength of these two columns shall be more than 1.4 times the design strength of this beam. This has to be checked for each beam column joint except those at the roof level in the buildings more than 4 story tall. Why? At roof level you will suddenly have a column. Once we have the relative strength of beam and column in place, we shall be designing the longitudinal reinforcement. So, in case of a circular column, we have to use at least 6 reinforcement bars, be it any diameter. But when it comes to rectangular columns, again, or all the columns, even circular columns for that case, the minimum longitudinal reinforcement as per IS 456 as well as those satisfying the relative strengths of beams and columns at the joint. Why? Typically what you will realize that the condition enforcing relative strength of column being more than 1.4 times that of the beams is enforcing in most of the cases. We will look into that as we see the solved example. At some point you may have to build a column which has some projection outside in this manner. In that case, if your projection has longitudinal and transverse reinforcement which are satisfying the guidelines of IS 456 as well as IS 13920, then in that case we will consider the contribution of that projection in the seismic resistance of the column. But if only IS 456 is followed while obtaining the reinforcement requirement for these projections, then in that case the seismic resistance of these projections shall be ignored and the column area shall be taken only up to this point. Now, once we have the longitudinal reinforcement requirement for the column, then we shall also have to splice the longitudinal reinforcement, because the steel bars are available in a limited length. So, you need to splice them. For that, the most common type of splice is lap splice. In that case, the minimum lap length has to be equal to the development length of the largest longitudinal bar in tension. Based on the longitudinal bar diameter, it can be expressed as a factor multiplied with phi, that is the bar diameter, but it roughly comes to be around 48 to 50 times of bar diameter in most cases for commonly used bars. At the same time, at that lap location we need to use closed links with a spacing not exceeding 100 millimeters. So, these ties or the transverse reinforcement will have a spacing less than 100 millimeters in those splice regions, and the splicing shall be done only in the central half of the clear column height, which means that within the clear column height the top 25% and the bottom 25% will have no splicing. The 50% of the column length shall have all the lap splicing. Also, lap splices will not be provided within a joint or within a distance of 2D from the beam face. This is very similar to the lap splicing in case of beams. Further, you cannot be splicing more than 50% of the longitudinal reinforcement at the same time, which means at any splicing location not more than 50% of the steel bars shall be spliced. Further, if your longitudinal steel bar has diameter more than 32 millimeters, you have to mandatorily use mechanical couplers for splicing the reinforcement. When it comes to mechanical couplers, they need to conform to IS 16172 and they should be capable of developing a specified tensile strength of spliced bars. You can also provide them within the distance 2D from the beam face or from probable steel yielding zone. Another type of splicing is the welded splices, which has similar regulations as the lap splices. You should not be providing it within a distance of 2D from the beam face or in a location of possible steel yielding. You cannot splice more than 50% of the area of steel bars at the same section, and welding of links and ties to longitudinal reinforcement is not permitted in any seismic zone. Now, once we have the longitudinal reinforcement and the splicing understood, let us try to understand how do we design columns for shear. So, when we are designing column for shear, in this case we shall be taking two criteria. One is the first criteria is our factored shear force demand obtained as per linear structure analysis. We have seen this in case of beams, we will also implement this in case of columns. Then the second criteria is factored equilibrium shear force demand when plastic hinges are formed at both ends of the beam. It is slightly different from the criteria which we have seen in case of beams, where we also had factored shear force due to dead load and live load plus the factored equilibrium shear force demand. Here that factored shear force demand due to dead load and live load are not available, because on a column typically you will not have a live load and the dead load of the column will be adding very little to this factored equilibrium shear force demand. So that is why only the factored equilibrium shear force demand is chosen. Now we will again consider two cases for sway to right and for sway to left. The expressions are given over here. So what has been assumed, that when there is a sway to right, then in that case the section at A, which is from the beam framing on this side, is undergoing sagging and the beam on the B side is under hogging, and therefore what you understand over here, for sway to right Vu is calculated as 1.4 times of MUAS, that is the moment of resistance of the beam on the A side in sagging plus the moment of resistance of beam on the B side in hogging, and this has to be divided by the height of the story. Similarly, for sway to left it is 1.4 times of MUAH plus MUBS divided by HST. Now based on these two cases you shall be able to choose the larger value of Vu, and then from these two criteria you should be able to obtain the design shear force in the column. Once the design shear force is obtained, we shall calculate the design shear force capacity as per IS 456 and compare and see whether the column is safe in shear or not. Then the design for shear will have to finally yield the transverse reinforcement. So in case of circular columns we shall be using either a spiral or circular links. In case of rectangular column we shall be using rectangular links, and in all these cases we have to enforce that there is a 135-degree hook at the end as shown over here, which means that any stirrup or tie shall has to be bent by 135 degree, and the extension after that bent should be at least 8 times the diameter or 75 millimeters, and that has to be embedded in the confined core concrete. Okay. Then if your longitudinal bar diameter is up to 32 millimeters, then the minimum diameter of the link is 8 millimeters, and if your longitudinal bar has diameter more than 32 millimeters, which is not very common, then in that case you shall be using minimum 10 mm ties or links. Further, in some cases when you have a larger column, then in that case the maximum spacing of parallel legs can be more than 300. Let us say that we have a column with dimension 500 mm by 500 mm. Then if you put a single closed tie, let us say of 8 mm dia or 10 mm dia even, then in that case if you remove the clear cover, what you get is the center to center spacing of the parallel legs of the link, and since it is a 500 mm by 500 mm column, that center to center spacing is much larger than 300. So in that case you need to either provide a cross tie as shown in this very diagram. You can see a cross tie provided over here, or you can provide an overlapping tie over here. So in this case there is one big closed tie like this, and then there is one overlapping tie shown over here. So that can be provided. However, in this case they have used two cross ties actually, but an overlapping closed tie can also be provided. Now the maximum spacing of link, that is of the ties over the column length, shall be at least half of the lateral least lateral dimension. This is except for a special confining reinforcement. We will learn more about a special confining reinforcement later, but let us say that the column is 400 millimeters by 500 millimeters. Then the links or the ties will be spaced at maximum of half of the least lateral dimension. The least lateral dimension is 400 mm in this case, so it has to be 400 by 2, that is 200 millimeters. You cannot have a spacing of these links more than 200 millimeters. Now, once you have the design for shear and the transverse reinforcement guidelines known to you from the ductile detailing perspective, it is time that we look into the design steps related to seismic design of columns. So, the first step would be to arrive at the column cross section. How will you arrive? One is by experience you can tell, okay, let us start with this column dimension, let us say 350 by 400 or 400 by 400 and so on, but that column cross section must satisfy the ductile detailing requirements for column geometry, which we have discussed in today's class, and it is given in section 7 of IS 13920. After arriving at the column cross section, we obtain the design axial force, design bending moment and design shear force, PU, MU and VU. How do we obtain that? First thing is by using linear structure analysis, that is we apply dead load, live load and seismic load in a numerical program. You can always arrive at the design forces and moments in the column. But since we are using capacity based design, that is we are following weak beam strong column hypothesis, we need to find out the moment carrying capacity of beam, which we have found out in the last class, and based on that we will decide about the design bending moment for the column. Once we have the design forces and moments known to us, we shall classify the column whether it is a short column or long column. For that we will calculate the effective slenderness, that is the ratio of effective length to the dimension of the column. We will look more about this. If the effective slenderness exceeds 12, we call it a long column, else it will be a short column. After that we also design every column for a minimum eccentricity. So, the minimum eccentricity as per clause 25.4 of IS 456 is given by this expression, which is the unsupported length of the column divided by 500. So, it is the clear height of the column divided by 500 plus d by 30 or 20 mm, whichever is more, and this has to be considered in each direction separately. How do you calculate the eccentricity? The eccentricity is calculated as the ratio of the design bending moment to the design axial force. So, if your eccentricity is less than this minimum eccentricity, you need to increase your moment so that your minimum eccentricity criteria is satisfied. Now, once we have the design forces and moments known to us, the classification of column ready with us, it is time that we design its longitudinal reinforcement. In case of short columns, that is when your effective slenderness is less than 12, then in that case we will calculate these two ratios. One is PU by FCK BD, the design axial force divided by a product of characteristic compressive strength of concrete, width of column and depth of column. The second term is MU by FCK BD square, that is the design bending moment divided by a product of characteristic compressive strength of concrete, width of column and a square of depth of column. And once we have these two factors known to us, we will utilize the relevant chart from SP16. Here we have one more additional reference which I would like to tell you, that you keep a copy of SP16 ready with you while we take you through the illustrative example. So, we will use the relevant chart from SP16. SP16 has a number of charts which are for given values of Fy, that is the yield strength of steel reinforcement. D dash by D we will look about that, and based on these we shall be able to obtain required percentage of longitudinal steel as a ratio to the characteristic compressive strength of concrete. So, we will get it as P by FCK. Once we have the P by FCK, we can obviously calculate P because FCK is known to us, and then we can check it whether it is satisfying the minimum and maximum reinforcement values or not. The minimum longitudinal reinforcement in case of column is 0.8% of the cross sectional area. This is based on clause 26.5.3.1 of IS 456. The maximum longitudinal reinforcement in case of column is 6% of the cross sectional area. But since you will have lattice splices at some locations, and since lattice splicing of not more than 50% of reinforcement is allowed, your limit of maximum longitudinal reinforcement practically goes down to 4%. This gives you a scope to have lattice splices in 50% of the reinforcement. Alright, so now we have already checked our required steel against minimum and maximum reinforcement values. Then we shall provide longitudinal reinforcement. The minimum diameter shall be 12 millimeters and the maximum spacing shall be 300 mm. And after providing the longitudinal reinforcement, we should again check whether it satisfies the minimum and maximum longitudinal reinforcement requirements or not. While solving the problem for beam, we have assessed the required steel against minimum and maximum reinforcement values, but we have not assessed the provided longitudinal reinforcement. In reality, you should be evaluating the provided longitudinal reinforcement as well against the minimum and maximum longitudinal reinforcement requirement. Okay, and the provided longitudinal steel must satisfy ductile detailing requirement, and the splicing and anchorage may be designed and detailed suitably. Okay, so having understood the design of longitudinal reinforcement in case of short column, it is not very difficult for us to understand what happens in case of long column. In case of long column, you now have an additional moment which is obtained based on clause 39.7.1 of IS 456. Only while going for these two factors or these two values, instead of mu, now you have mu plus this additional moment coming into picture, and you enter SP16 with these two values now, and you do the same process. You obtain what is the value of P by FCK required. From there you know the percentage of steel which is required. You check it with the minimum longitudinal steel and maximum longitudinal steel that is permissible, and then you end up providing longitudinal reinforcement. Alright, the steps are the same. Now, after designing the longitudinal reinforcement, we will check the adequacy of section, because usually the columns will have biaxial moment as well. So, in this case, we shall calculate the value of Pu upon Puz. Pu is the design axial force in the column. Puz is calculated using this very expression, which is available in clause 39.6 of IS 456. Then we will define a constant alpha n which depends on this factor Pu upon Puz. So, if Pu upon Puz is less than 0.2, alpha n shall be equal to 1. If this value lies between 0.2 and 0.8, alpha n will vary linearly from 1 to 2 and can be obtained using linear interpolation. And for Pu by Puz greater than 0.8, alpha n will be equal to 2. Then after finding these, we shall find out the moment carrying capacity of the column in both the directions. How will you find? Now you know what is the steel reinforcement you have provided. So, from the P provided and based on this value of Pu by FCK BD and other values, you go to the relevant chart in SP16 and you end up obtaining MUX1 and MUY1. Okay, so I suggest that you have a copy of SP16 with you while going through these lectures. This will be very useful to you. You can obviously do it from the mechanics perspective, but that will consume a lot of time and involve a lot of iteration. So that's why the charts provided in SP16 are really useful. Then after finding these values MUX1 and MUY1, it's time to check the adequacy of section under combined axial load and biaxial bending. So you check this very expression shown over here, the value should come less than or equal to 1. If it comes more than 1, the section is not adequate and you need to redesign the section, mostly increase the cross section or the steel in the section. Once the adequacy of section is established, we now start the design for shear. For designing for shear, in the design for shear, first of all we calculate the design shear force. The design shear force shall be the more critical of the two criteria. The first criteria is factor shear force demand as per linear structure analysis, and the second criteria is factor equilibrium shear force demand when plastic hinges are formed at both ends of the beam. We have described these earlier, and then we calculate the stress. The nominal shear stress in the column shall be equal to VU, that is the design shear force, divided by the BD. B is the width of the column and D is the effective depth of the column. It will be more clear when we do the calculations as part of our illustrative example. Then we calculate the design shear strength of concrete. It is obtained using table 19 of IS 456, and it depends on grade of concrete and percentage of steel reinforcement, but for column it also depends on design axial force and gross area of column. There is a multiplying factor which is given by clause 40.2.2 of IS 456. So refer to this and try to find the value of design shear strength of concrete. Then the maximum shear stress tau C max, which depends only on grade of concrete, can be obtained from table 20 of IS 456. Now if your nominal shear stress is less than equal to the design shear strength of concrete, it implies that the concrete is able to resist all the shear. So you need to provide only the minimum transverse steel reinforcement as suggested by the code. If your tau V lies between tau C and tau C max, then in that case our concrete is itself not sufficient, but the section can take the shear. That's why we will be designing the transverse reinforcement. If your tau V is further higher than tau C max, then we need to redesign the section. In most cases we have to increase the cross sectional area. So the same has been explained over here, all the three cases, how to design the transverse reinforcement. Now the provided transverse steel must satisfy ductile detailing requirements. In the upcoming class, we will look into an illustrative example which shows or illustrates the design steps that we learned in this class related to seismic design and ductile detailing of reinforced concrete columns. Thank you.